Hi class, we are now on chapter 9. This is going to be covering 9.1 and 9.2. So we're going to look at electrons in atoms in the periodic table. There's two important models that help us understand the behavior of the elements. There's the Bohr model and the quantum mechanic model. These models help explain how electrons exist and how these electrons affect the chemical and physical properties of elements, basically the behavior also that we see. So Bohr and Schrodinger, Niels Bohr and Erwin Schrodinger, along with Albert Einstein, played an important role in the development of quantum mechanics. So, yet they were bewildered by their own theory of wave-particle duality. So let me explain. The electron, when they did these experiments, they found that an electron followed a certain set of, in a sense, behavior, and it made sense. But when they did other experiments, they found that the electrons did not follow at all what they were seeing, what evidence was showing, and they had no way to explain it. And this is where the wave-particle duality came from, where an electron behaves as a wave, and as other times it behaves as a particle. So that's what this duality theory of wave-particle duality comes from. All right, so we're going to look at electromagnetic radiation. What we can see is visible light, but there's a far more bigger spectrum of electromagnetic radiation. One of the things you see here with visible light is that when it goes through a prism, it's separated by its own distinct wavelengths, and those wavelengths for the visible light have colors to them. And also fireworks, even though this is flames here, this also explains the colors that we see in fireworks. So light is a form of energy, and it's described as a moving wave of magnetic and electrical potential. We're going to expand on that later. Visible light is exactly what it says, what we can see with the human eye. And we kind of just see, we see white light. But when you put a prism up to a certain light, and you put the beam through, you actually see a prism. Sort of, remember, think about rain, of a rainbow. It separates. So this white light will separate into the different colors based on this wavelength, and I'm going to get into what wavelength is. All right, so let's start out before I can discuss wavelength, but it's exactly what it sounds like. You see this is a wave, and we have a crest at the top and a trough at the bottom. And if you go in directly in the middle, half of a wave, that's the amplitude. We're not going to really spend too much time on amplitude though. But there are, you definitely should see height of wave, nothing to do with wavelength, frequency, or speed. This is just the intensity, but really we're not going to cover amplitude. I don't even know why it's there. I guess they have to cover it. Wavelength is this fancy little upside down V. It's called lambda. Distance, and you definitely should know this. Distance traveled between two successive peaks or two successive troughs. So what it means is the crest. We look at this crest and we would look at this crest, or we would look at this trough, and that's considered a wavelength. Okay, so properties of light. A wavelength, lambda, can either be in meters or nanometers. This is where these conversions are going to start coming in, but the good thing is you're only really pretty much dealing with meters or nanometers. Is the distance between two corresponding points. Frequency is this little fancy V, it's called nu, is the number of crests that pass a given point per second. The unit of inverse seconds. So when you see this is 1/seconds, or you can say inverse seconds, but this is also equal to hertz. So when you hear hertz, that means 1/seconds. Frequency has to do with number of crests. Remember, crests are the top. This is very simple. What you need to do is consider yourself sitting somewhere and count how many people walk by a certain light pole. Some will walk by very slowly, which is what you would see here. And then a bunch of people walk by very quickly. And in a certain amount of time, that's how you would count this. Okay, let's say in a minute, 10 people walk by a light post. But then, another light post, in 10 minutes, 25 people walk by. That's the difference. You either have a slow wave or a big wave, and that's the frequency of it. The frequency is how many of these people walk by that pole in a certain amount of time. So frequency times wavelength, so here we go, frequency times wavelength equals a constant, and that constant is the speed of light. It's either, some books have this as 2.998, others have this as 3.00 times 10 to the 8 meters per second. Remember, seconds, we use an S, we don't use SEC. So this is meters per second, and I have it down here. And you could also write it like this. So wavelength, these are wavelengths. Frequency, either how fast they're going or how slow they're going, equals 3.00 times 10 to the 8 meters per second. Now, this is a constant, meaning this number doesn't change. So if these are equal, that means that one of these has to go up and one of them has to go down, because this value here doesn't change. And it's C as a symbol. So if you have a higher frequency, you have a smaller wavelength, because the smaller the wavelengths are, the more waves that can go through at a certain time. But when you have a big wavelength, it's going to take a lot longer. So if you follow this little red dot, you can see how this one's going really quickly. So higher frequency, smaller wavelength. Less frequency, bigger wavelength. And these mean they are inversely proportional, which means exactly what I'm talking about here. If one goes up, the other one has to go down. That's what makes them inversely proportional. Okay, so frequency, there we go again with frequency. When we look at higher energy, so when we talk about just energy itself, energy, see how these are think of this as a curl. We have a very loose curl and then a very tight curl. These are high energy. This is a shorter wavelength, higher frequency, higher energy, because more can go through in comparison to the bigger wavelength. Where we get lower energy is longer wavelength, lower frequency, lower energy. These are terms you absolutely should know, because then you don't have to get stuck trying to break these definitions down. Once you get these definitions to match what is higher energy, what is lower energy, it will help you understand what exactly is happening here. So when you come here, you can see this is electromagnetic radiation spectrum. This is all we see. With the visible eye, we have this little tiny section here compared to everything. And on the spectrum over here, which is gamma rays and X-rays and UV light, these are higher energy. So UV light is higher in energy than visible light, X-ray is higher in energy than UV light, and gamma ray is higher in energy than X-ray light. When we go on the other side, visible is higher energy than infrared. Infrared is higher than microwave, and microwave is higher than radio waves. So we start out with the low, and so even in the visible, the colors change. Red is low energy in comparison to when you get over here. This is supposed to be like a purple. It looks like a pink, and it really shouldn't, but this is more of a purple. It's a deep purple color. I don't like that they did that. But so the blue and the purple. So if you think about it this way, blue, when you turn a stove on, your flame is blue. That's a very hot flame. In comparison to when you light a fire at a beach, a bonfire, the flame is red. Red is actually not as hot as a blue flame. So if you guys are physically in lab, unfortunately you're not, you would use gas. We use gas in our experiments, and the blue flame is hotter than the red flame. The blue flame also does not leave that black smoke of cinder that you would get with a beach fire on it. Okay, so again, let's go through this one more time. I'm just see this as the same page, but I want you guys to understand this. Wavelength, lambda, is the distance between two corresponding points. So either two mountaintops or two of the bottom valley parts, if that makes it easier to understand. Frequency is the number of crests that pass a given point per second. The unit of inverse, the unit is inverse of seconds, so 1 over seconds, and it's also known as hertz. So if anything is referred to as hertz, that's 1 over seconds. Frequency times wavelength equals the constant c, the speed of light. It either is 2.988, 2.998, or 3. I just rounded up because it's super easy. Who wants to deal with 2.998? This is a constant. This is a value that doesn't change. So in order for that value to not change, then the other values of frequency and wavelength have to change. One either goes up, one either goes down, but that 3.00 times 10 to the 8 meters per second does not change. All right, so now let's discuss the wave particle duality of light. So light is able to function as both a particle and a wave based on the experiments that were conducted, and this is exactly what they saw. Some experiments they saw light as a particle, and at other experiments it says it was more like a wave. So now they have realized that they need two different theories in order to explain the behavior of light. So under certain conditions, you can shine a light through a narrow slit, and what you will do is you will see it behave as a wave. But you shine a light on a metal, and the spray of electrons that are ejected, the light behaves as a particle. So let me explain here. So we see, if we go back here, this kind of gives a nice visual of the waves. You can see the waves. So this is where the wave part of that wave particle duality comes from. But see, we can't see these moving with our eyes, so this is a better visual than that. But if we shine a certain amount of light at a certain energy value, what will happen is that electrons will get ejected from a metal, and that's what we start calling these particles. So this is where the wave particle duality comes from. It's a multi-personality of light, is what they say. So light behaves as a wave or as a particle, depending on what we need with it and how we set up the experiments and what we're trying to observe from it. So electromagnetic radiations, we call this photons of light. A particle of light is called a photon. We think of a photon as a single packet, so a single packet of light energy. This is where we view light as stream of particles instead of a wave. So this is that visual here. So all of these here we call photons here. All right. The amount of energy carried in the packet depends on the wavelength of the light. So the shorter the wavelength, remember, the shorter those wavelengths, the greater the energy. Light waves carry more energy if their crests are closer together. That's like a tight curl. Higher frequency and shorter wavelength. Violet light, that's what that pink is supposed to be, is more of a violet, has a shorter wavelength, carries more energy per photon than red light, or longer wavelength, which, remember I told you, red is on the spectrum of being considered not as high energy as blue and purple here. So when we shine this is where we start talking about, we shine particles, a property of light. So we have this photons, we call these photons. All right, so electromagnetic radiation is a form of energy that travels through space at a constant speed of 3.0 times 10 to the 8 and can exhibit either wave-like or particle-like properties depending on how we want to see this and what we're observing, basically experiments. The wavelength of electromagnetic radiation determines the amount of energy carried by one of its photons. The shorter wavelength, the greater the energy of each photon. The frequency and energy of the electromagnetic radiation are inversely related to its wavelength. So again, let me just summarize. This is electromagnetic spectrum radiation. This is lower energy. This is higher energy. And everything that's on this side is higher energy compared to this side. These are the waves that match that energy. And you can see at the end, these are very, very tight, very short waves. They have higher energy. When we look at visible, red is the lowest energy in comparison to purple or violet color. Violet has the highest energy over blue and everything. So everything that's one next to it is higher energy than what's previously next to it. And that's it.